This video will cover the mechanical advantage of 5 of the 6 types of simple machines. The mechanical advantage of levers will be covered in a separate video. Mechanical advantage is abbreviated MA, and it is defined as the number of times a machine increases the effort force. The formula for mechanical advantage is resistant force divided by effort force. Mechanical advantage numbers can be used to indicate what is going on in a specific setup. A mechanical advantage greater than 1 shows that force is increased. A mechanical advantage less than 1 shows that only distance is being increased, with a mechanical advantage equal to 1 showing only the direction of the force is changing. Now here we have a mechanical advantage problem. A worker applies an effort force of 20 newtons to open a window with a resistant force of 500 newtons. What is the crowbar's mechanical advantage? Now remember that mechanical advantage is the resistant force divided by the effort force. Our problem has given us both the resistant and the effort force. We know that our effort force is 20 newtons, and we know that our resistant force is 500 newtons, both being stated in the problem. We will apply that to our equation. We will have 500 newtons divided by 20 newtons. Our mechanical advantage is 25. There are no units attached to this number. Now here we have a mechanical advantage problem where we are asked to find the effort force needed to lift a 2,000 Newton rock using a jack with a mechanical advantage of 10. Now when we look at this problem, we will notice that we have an effort force that is unknown, a resistant force of 2,000 newtons, and a mechanical advantage of 10. The formula that we will be using is, now that's where the algebra portion of physical science comes in. If you're not comfortable taking an equation and rearranging it in order to get it in a new form, then take that existing equation and fill in the components from our problem and do algebra and solve for x. We know that our mechanical advantage is 10. We know that our resistant force is 2,000, and here we have x. Now by doing this algebraically, we would get 10x equals 2,000, and then we would take our 2,000 divided by 10, and we would get our x as being 200 newtons. So again, most of our physical science problems can be solved by basic algebra. Now in dealing with mechanical advantage, a machine's mechanical advantage is going to be the number of times the force exerted on a machine is multiplied. The ideal mechanical advantage does not have units because all units cancel out. So ideal mechanical advantage would equal the output force divided by the input force. And we are going to look at how mechanical advantage and ideal mechanical advantage problems play out for the various types of simple machines that exist. The first simple machine that we will look at is an inclined plane. An inclined plane is a sloped surface that's used to raise an object. The ideal mechanical advantage for an inclined plane is calculated by taking the length of the plane divided by the height the object will be raised. Here we have an ideal mechanical advantage problem dealing with inclined planes. How much force must be exerted to push a 450 Newton box up a ramp that is 3 meters long and 1.25 meters high? Now we know that our effort force is our unknown, our resistant force is 450 newtons, the length of our plane is 3 meters, and our height is 1.2 meters. Now I have sketched out our little scenario here. We have our inclined plane that's 3 meters long. The height is 1.2 meters. And then we're pushing a box that has 450 newtons. And we need to know how much effort this individual needs in order to push this box up the inclined plane. The first thing we need to do is we need to calculate the ideal mechanical advantage. Now, the ideal mechanical advantage is the length divided by the height. We have our length as 3 meters and we have our height as 1.2 meters. So our ideal mechanical advantage would be 3 divided by 1.2, or a mechanical advantage of 2.5. Now that we have our ideal mechanical advantage, we can then use that information along with our resistant force to calculate our effort force. So, if we remember that our equation for our mechanical advantage is resistant force divided by effort force, and we've calculated our mechanical advantage as being 2.5, we know from our problem that 450 is our resistant force. We need to solve for our effort force. So we get x times 2.5, and we get 2.5x equals 450. We take our 450, divide it by the 2.5, and x would be 180 newtons for our effort force. The second type of simple machine is a screw. Now, a screw is an inclined plane that is wrapped in a spiral around a cylinder. It multiplies the effort force by acting through a very long effort distance. The closer the threads are, the greater the mechanical advantage the screw has. A wheel and axle is a simple machine consisting of an axle to which a wheel is fastened so that the torque applies to the wheel as the wheel winds a rope or chain onto the axle. Now, the ideal mechanical advantage is still abbreviated IMA. Now, the effort force is usually applied to the wheel where the axle moves less distance but with a greater force. The formula for the ideal mechanical advantage for a wheel and axle is the effort radius, which is the wheel's radius, divided by the resistant radius, which is the axle's radius. Now here we have a wheel and axle mechanical advantage problem dealing with a machine that makes pasta. The crank on the pasta maker has a radius of 20 centimeters. The turning shaft has a radius of 5 centimeters. What is the ideal mechanical advantage of this pasta maker? Well, remember that the ideal mechanical advantage formula is the effort radius divided by the resistant radius. Now, the effort radius was 20 centimeters and the resistant radius was 5 centimeters. 20 divided by 5, and we would have an ideal mechanical advantage of 4. Here we have a mechanical advantage problem dealing with the steering wheel. Now, a steering wheel requires a mechanical advantage of 6. What radius does the wheel need to have if the steering wheel column has a radius of 4 centimeters? Well, this is a wheel and axle problem, so our mechanical advantage is going to be our effort radius divided by our resistant radius. From our problem, we know that our mechanical advantage is 6, our effort radius is our unknown, and our resistant radius is going to be 4. We're going to plug that information into our equation where we have the mechanical advantage being 6, our resistant radius being 4. Here we would have our x, and so we would have our 6 times 4 with our effort radius being 24 centimeters. A wedge is a simple machine where we have a moving inclined plane with 1 or 2 sloping sides. Now, with a wedge, the longer and thinner the wedge is, the less the effort force will be needed to overcome the resistant force. We will not be doing any calculations with wedges. A pulley is a simple machine that consists of a wheel over which a pulled rope or chain runs. Now this is run to change the direction of the pull used for lifting a load. Combinations of two or more pulleys can work together to reduce the force needed to lift a load. So the ideal mechanical advantage for a pulley is going to equal the number of supporting ropes present on the pulley. And as we look at some of these diagrams, here we have an ideal mechanical advantage of 0. Now here we have the rope, but we pull the rope outward, so we only have that one area here, and so that's an ideal mechanical advantage of 1. Here we have 1, 2, this pulls out, so this has a mechanical advantage of 2. Here we can see what block and tackles look like, and these are combinations of fixed and movable pulleys, and they help to increase the mechanical advantage. Now here we have a movable pulley, and here we have our fixed pulleys. So they may or may not change the direction, and so how do we know the mechanical advantage? Well, we're going to look at the support ropes. We have 1, 2, 3, 4. Now this part right here is going to be pulling out and does not count, so we have a mechanical advantage of 4.